Okay, so here is our review for exam number 3 for CE 315. This should be being played for you on Wednesday morning. I'm also going to post it on Blackboard so you can look at it at your leisure. This is the same type of review that I've done before. So the material in these slides is meant to help you study, but does not represent everything that you should know. Remember to read the book, including especially the worked examples. Those are good examples of things to look at for worked problems. Study the lecture notes and your personal notes, and study the homework problems and the solutions as well. You will be given one side of an 8.5 by 11 sheet like you have been for the past exams. Remember to write it in pen. Definitions, concepts, and equations are fine. Steps to following problem solutions are fine, but please no worked out problems, and you will hand this in along with your test. This is your responsibility to make sure that it gets in with your test. So also definitely put your name on it this time. Because Sarah Murphy will be proctoring the exam, and she might not be quite as careful as I am with your equation sheet. So make sure you put your name on it and make sure you turn it in. If you do not do that and she does not have it, you will be responsible for not getting it turned in. So please do that. So this exam will be over chapters 6, 7, and 8. We're going to start with the momentum equation. Again, this is only going to go up through section 6.4. So that's the chapter with jets, vanes, pipe bends, and nozzles in it. So stationary control volumes. I'll mention that again in a minute. So this, if you remember, this chapter was on the momentum equation, and we are focusing on surface forces. These are forces that require physical contact between interacting bodies, and in this case, it's the fluid and other objects. And so we're looking at the types of problems and forces that you would see in this red box here on this slide. We spent quite a bit of time talking about how the momentum equation is related to the forces. And so here we're showing that the sum of the external forces is equal to the mass times the acceleration, but that we can rewrite that as being the time derivative of the momentum, which is how this equation generally works out. So the momentum equation does come from the Reynolds transport theorem, where the extensive parameter, capital B, is equal to the momentum, mv, and the intensive parameter is the momentum divided by m. So it's just the velocity. So when you plug this into the Reynolds transport theorem, which you can see in the upper equation here, you see that we have the sum of the external forces is equal to two integrals, one over the control volume and one over the control surfaces, the important control surfaces. And this reduces to an equation that is the sum of the forces acting on the matter inside the control volume equal to the momentum accumulation. That is the time rate of change of momentum of matter inside the control volume. And as we've mentioned before, this is normally 0 for our situations, but not always, not in general. And that the momentum accumulation is added to the net momentum outflow. So that's the outflows minus the inflows, and that's the net rate at which fluid flow transports momentum out of the control volume through the control surfaces. And so this is just a table that shows our working equations, and you should be familiar with the simplified equation here at the bottom here, and what the various terms mean and how you use this to do various problems. And in particular, we're going to be interested in stationary control volumes and jets, vanes, nozzles, and pipe bends. So make sure you have a look at those types of problems and be sure you know how to do each one of them. The second chapter is chapter 7, which is the energy equation. Again, look at the learning objectives. We basically started talking about energy and work. Work was force times distance. We then moved on to power, which is the quantity of work or energy that is either used or put into a system per interval of time. So it's basically the work, the derivative of the work with respect to time, or W dot. And there were two special ways that we could, two machines basically, that we could use to either extract energy or put energy into the system. So a turbine is basically a machine that is used to extract energy from a fluid flow, from a flowing fluid, and a pump is used to put energy into him. So we went through this nasty equation, but basically I want to show you that for a closed system, the amount of the change in energy per unit time is basically equal to what's called Q dot minus W dot. So if you look at the conservation of energy in the second law of thermodynamics, you can see that that's a balance of work and energy, and that the change in energy is basically an increase in the energy stored in the system, and that has to equal the amount of energy that entered the system by heat transfer minus the amount of work left by the system to do work. And so the time derivative of that is just the rate of change of Q minus the rate of change of W. Now this is going to be important because this dEdt shows up in the Reynolds transport theorem, because capital E is our extensive parameter and E over M, the energy per mass, is the intensive parameter. And we after a nasty derivation, we get this equation that needs to basically be simplified. You are definitely not responsible for doing this derivation. It's quite difficult, but you should definitely understand how to use this simplified equation and what the major assumptions are. So you can see the assumptions over here on the left, and we note that we are, as usual, it looks a lot like the Bernoulli equation with some differences. We have these kinetic energy correction factors, these alphas, and then also the velocities now are average velocities instead of regular velocities, regular speeds. And so on the left-hand side of the equation, we have ways of putting energy into the system, and on the right-hand side of the equation, we have energy coming out of the system, and that's why on the left we have the pump head, the HP, H sub P, and on the right-hand side of the equation we have the turbine head, H sub T, and the head loss. Remember that we are going to, from here on out in this semester, we're going to be trying to account for losses in systems, and so the head loss is kind of all the losses due to heat and viscosity and things like that that are extracting, and turbulence that's extracting energy out of the flow. So we've got a nifty equation where we're able to include pumps, turbines, and the head loss now. Note that this equation is actually in meters, dimensional homogeneity, or it's in units of length. Could be either feet or meters or any unit of length for that matter, but it's not in pressure. This is the head equation, which is in units of length. So the other thing that we talked about was how to calculate the amount of power that is supplied by a pump or that is basically being extracted by a turbine. And we've got an equation here at the bottom of this table that the power is equal to the mass flow rate times gravity times H, or the specific weight times the volume flow rate times H. So this has a way of relating power to the head in a system. And finally, we for the calculations, we are able to also add mechanical efficiency into the problems, where we note that the efficiency eta is defined to be the power output from a machine over the power input. So when we look at the equations down below, we can see that the pump is always basically getting less energy than the shaft, because of basically because the efficiency has to be less than 100%. So, and likewise for the turbine. So you need to, what I advise you to do is to always think physically about these problems when you're using the efficiency, and make sure that you are not getting free energy out of the system, and that this efficiency really is a cost to the system. And that an efficiency less than 100% basically says that there are losses within your machine, probably due to friction and heat loss and things like that. And finally, the final concept in this chapter was the concept of the energy grade line and the hydraulic grade line. And here are the definitions. Energy grade line is the velocity head, pressure head, plus the elevation head, all three of those terms. And the hydraulic grade line is just the pressure head and the elevation head, which of course is just the piezometric head. So when we look at these diagrams, there's a number of these diagrams in the textbook that you should have a look at. Here's a simple one that shows that in the upper left, at the top of the reservoir, the EGL and the HGL are actually equal because there's no velocity. The velocity is very small. But as soon as the fluid starts to flow through the pipe, the fluid speeds up and you have some velocity head. Now, if the velocity is constant through this whole pipe, then the velocity head is constant, and the difference between the EGL and the HGL must be constant along the whole pipe. But also, what you can see is that there are also head losses. Kind of in the upper part of the diagram, you can see H sub L is an imperfect. Let me back up here. The horizontal line at the top that the head loss is referenced to is a system that's perfect with no head loss. So anywhere along this pipe, you would have the same amount of energy if there was no energy being lost. But if it's a very long pipe and there is head loss, then the further and further you go along the pipe, you have less and less energy because the head loss is being subtracted, or is using energy out of the system. So this just kind of gives you an idea of how to kind of diagram what kind of energy you have in the system, the EGL and the HGL. And as it says in the textbook, it also gives you a means to look for any problem areas like negative pressure or really low pressure in the system that might be causing cavitation. All right, so the final section is Chapter 8 on dimensional analysis and similitude. The primary things we talked about dimensional homogeneity again. This was just really a repeat of Chapter 2, I believe. And but we also went further this time and did dimensional analysis. We also talked about why it's important in engineering. A lot of times we work on models in engineering, models, prototypes, which we can do quite accurately and without compromising any of the physics. So it's important in these problems to determine what the fundamental dimensions of measurement are, and which fundamental dimensions are typically used in fluid mechanics. And for our purposes, really, we're only having to deal with mass, length, and time. And so when we realize this, we can move on to the Buckingham pi theorem, and we can determine the number of dimensionless pi groups that are going to come out of any sort of given analysis. So if we have n number of variables that are involved in a problem, and when we look at the dimensions of those variables and sum them up as m, then if we take simply n minus m, we're going to have that many dimensionless groups at the end of our analysis. So we looked at 3 different methods: step-by-step, exponent, and repeating variable. And I'm going to require you to learn the repeating variable method because I think it's the most straightforward and the least ambiguous of all 3 of the methods. And I also wanted to note that if you kind of include all the variables we've been talking about, force on the left-hand side, and then force being a function of all these different parameters that we've talked about, length, I think that's length, diameter, well, in any case, if you count these up, you've got 10 variables. If you realize that they only have 3 dimensions in different combinations for all of them, then we realize that we can only have 7 pi groups. And so when the analysis is done, these are the common pi groups that you get: the pressure coefficient, shear stress coefficient, force coefficient, and then the Reynolds, Mach, Weber, and Froude numbers. So these are important to know and be able to use. They're important because we can solve problems of similitude using these values sometimes if they're appropriate for the given problem. And so there are 2 different types of similitude. There's geometric similitude, which is just a perfect scaling of a model from a prototype. And then dynamic scaling, it actually just says that the forces on the 2 objects, the model and the prototype, have to be equal. And that allows us to solve problems and compare the different variables that go into working on models versus prototypes, and how we can do a good simulation on a model that reveals the important physics on the actual prototype. So there's a number of sections at the end of the book that you should look at, but also look at your homework problems that you did for this week. You'll likely be asked to do a similar type of problem or 2 on the exam. So that's really it. If you have any questions, please contact me this week, either by email. As I mentioned before, you can send me a Skype invitation. Note that my Skype address is actually the same as my email address. So if you're going to send me a Skype invitation, send it to my email address because it's the same. So remember that I'm available on Skype from 10 to 11 on Thursday, the day before the exam. That's Thursday the 15th, and I'd be happy to chat with groups of you. That would be best if you guys could get together in groups and give me a call if you have any last-minute questions. But email should be working as well. So good luck, everyone, and have a great Thanksgiving. Drive safely, and we'll see you guys after the break. Okay.